These are the frequently asked questions for Algebra 2 for Section 11-2, Day 2, starting with number 23. Number 23 says we have a group of 30 students from your school. It's part of an audience for a TV game show. The total number of people in the audience is 150. What is the theoretical probability of 3 students from your school being selected as contestants out of 9 possible contestant spots? When I'm reading this through, I'm really focusing on my denominator first. I want to use that counting principle to figure out what is the total that I'm looking at here. And everybody in the audience altogether is 150. And there are only 9 contestant spots. So we've got 150 to choose from, and we just need to think, well, does order matter to anybody? Well, if you're going to be a contestant on a game show, you don't care if you're the first person chosen or the 9th person chosen. Obviously, you'll get a little worked up and a little anxious waiting, but you don't care. You just want to make it on stage. So that means that's a combination. Order does not matter. Now, what we have to do for the numerator is what we talked about in class. We're going to have to deal with what we want to happen and then what we need to make sure that we have enough people up there on stage. So focus on what you want first. And what you want is the probability that 3 students from your school are going to be selected. Again, we're going to use combinations because you don't care about the order, but there were 30 students that came from your school. And you want 3 of those to be chosen. Now that has to happen, but you know what? That's not enough. How do I know that? That's only 3 people up on stage, and they want 9 people up on stage. So not only do those 3 people have to get selected, but we're going to have to think of it as 3 from your school and some other people. So that's going to mean multiplication. We need these to all happen at one time. Now, if 9 of them have to be on stage, and only 3 of them came from your school, that means 6 of them have to be people that don't come from your school. So you go back up there and you see there were 150 people in the audience, 30 of them were from your school, and that tells you 120 of them were not from your school. And now you have what you need. Now these might, in fact, these are going to come out to be some pretty large numbers here. You might want to try and punch this in all at one time so your calculator doesn't have problems with getting all the big numbers on here. To do that, make sure that you use grouping symbols for your numerator and your denominator. So extra sets of parentheses with this one should help you out a lot. In fact, it wouldn't hurt to put the parentheses, in fact, you're going to need those around your combinations right here as you punch that in as well. You certainly could punch in 30, choose 3, write down the answer, punch in 120, choose 6, write down the answer, multiply those together, figure out what 150 choose 9 is, and then divide it all by that. But I think you'll have pretty good luck here if you use some double parentheses. And that comes out to 0.179 or about 17.9% when you do that. So don't forget about the fact that you have to have 9 people up on stage. You have to complete what you need up on the stage. Then for 24 through 27, it says, suppose that a dart lands at random on the dartboard shown at the right. Find each theoretical probability. And I take a look at this dartboard and I realize we're talking about geometric probability here. And the reason we're talking about geometric probability is because that's 2-dimensional. You know, it has area, it has length and width. So for number 24, it says we want to find the probability that the dart lands in the bullseye. Well, everything we see up here is a circle, and we have to remember that the area of a circle is pi r squared. Now really, that's all we get with this one because they're not going to tell us what that radius is. They're just going to use r. Now, if, as I'm going through this, you're thinking, oh my gosh, where are the numbers? I wish I had more numbers with this. This problem will work if you just say, you know what, I'm going to say r is 1. And as long as you're consistent all the way through the problem and you say, okay, this is a 1, this is a 1, this is a 1, and this is a 1, you'll be perfectly fine. Consistency works with probability. But I'm going to go ahead and do this the way it was intended with leaving the variables in there, and I think you'll be pleasantly surprised with how everything comes out. So the dart landing in the bullseye, we know the area of that little region in there that has the 20 points is going to be pi r squared. And you're supposed to put the radius in, but the radius is already there. So that's just going to be pi r squared. And then what we have to do is go ahead and divide that by the total area of the dartboard. So if this is 1r for the radius, we have another one here, and another one here, and another one here. So from center to on that outside green ring is going to be 4r for the radius. So big green, 4r is our radius. So when we put that into pi r squared, that becomes pi times 4r squared. And that will give us 16 pi r squared. Don't forget that you have to square both the 4 and the r. We are going to square the entire radius. So 16 pi r squared. Now, good news. When you look at this, you'll notice, hey, I've got all multiplication on the top and all multiplication on the bottom. And if you're saying to yourself, wait a minute, Cedar Home, there's a power there too. There is, but powers are just multiplication. So your numerator here is pi times r times r. That's what that is. And your denominator is 16 times pi times r times r. Well, that's all multiplication, and we can cancel. Canceling is a form of division. So we're going to be able to take out the pi's, we're going to be able to take out the r squareds, and remember, in those positions you always put a 1. Anything that you've canceled means you've divided it out and it's a 1. So all we're really left here is 1/16th, and that is the answer to number 24, 1/16. Number 25 says, the dart lands in the green region. All right, so we've got a couple of green regions that we have to look at here. And as you look at those green regions, you realize, well, it can't land in both at once. You know, it has to land in one or the other. So I'm going to go after the small green region, the big green region, and then I'm going to have to add those together. If it can't happen at the same time, it's an or situation. An or indicates that we're going to have to add. All right, so small green. I want the area of the small green ring, which kind of looks like a donut. So I think about the fact that the radius of the entire circle out from that green ring is going to be 2r. So that would be pi times 2r squared, or 4 pi r squared. But I can't include my little circle that I just used for the bullseye. Well, the good news is I already know what the area of that is. I had to find that area in order to do that problem. That was 1 pi r squared. So for the small green circle, if I have 4 pi r squared and I subtract a pi r squared, I will have 3 pi r squared. Now that's the small green one. The big green one, good news, I already did some of that math too. I have that sitting right over here for finding totals. But again, I don't want to include the whole thing. I'm going to have to subtract everything from the big yellow circle out. Now, again, that's not really hard to find because it's going to be a radius of 1r, 2r, 3r. So I have to subtract pi times 3r squared. And that's going to be subtracting 9 pi r squared. So if we have 16 pi r squared and we subtract 9 pi r squared, we will get 7 pi r squared. So that's going to be the big green ring. 7 pi r squared. All right, so what I have so far is the big green ring at 7 pi r squared, the little green ring at 3 pi r squared, and when you add those two together, because it's an or situation, it's one or the other, we're going to get 10 pi r squared. And again, that's going to be over our total of 16 pi r squared. So we're going to get 10 over 16, which will reduce to 5/8 for number 25. Number 26 asks for the probability that the dart will score at least 10 points. If it's going to score at least 10 points, what we need is the small green circle, because we can also use what's inside that, which is that small yellow circle. So we have a lot of math down here. Chances are pretty good that we've already figured out what the area of that small green circle is, and we did. That was 4 pi r squared. So for 26, we're going to need 4 pi r squared over 16 pi r squared. And that, of course, is going to reduce to 1/4. So now, one more to go. 27. The dart scores less than 10 points. So you take a peek and you say, all right, where up here are we talking about stuff that would be less than 10 points? Well, that's the 5 or the 2. And again, we've probably already done the math for that, because that's going to be the green and the yellow. Or, here's the easier way to think about it. In 26, we just said to score at least 10 points, that's going to happen 1/4 of the time. So instead of overthinking this one, we could just say, well, you know what, if 1/4 of the time you're going to get 10 or more points, and that's what at least 10 means, then how many fourths are you going to get less than 10 points? Well, it's going to be 3/4. So 1/4 of the time you'll get more than 10 points, means 3/4 of the time you're going to get less than 10 points. So we could have done a whole lot of math for that one too. But again, once you've calculated as much as you have, start to step back and say, okay, am I overthinking this? Is there an easier way to figure this out? So, like I said, there you absolutely could do a whole lot of math and get exactly that same answer, but you don't have to. Then the next one was number 29 through 32. It's a group that uses a Venn diagram here. It says in a class of 147 students, 95 are taking math, which is your M in the Venn diagram. And you'll notice 43 plus 52 does give you 95. And then it says 73 are taking science. So you look over here and you see, okay, 52 plus 21. And you realize these students right in this overlap here are taking both. They're taking math and science at the same time. So 52 of those people are doing that. And then, of course, we have 31 people out here that are not taking either one. Bad idea, by the way. 31 people that don't know what they're doing. So 31 of them out there. And we're supposed to find each probability. So for number 29, it says find the probability that a student is taking math or science or both. So what we would want to do is we want to say, okay, here's the math, here's the science, here's the both. We're just going to add all that stuff together. So 43 plus 52 plus 21. Just a good old-fashioned addition here. And we will get 116 people that are taking that. And then we need the total. Well, they already told us that in the word problem. They said in a class of 147 students. So this will be 116 divided by 147. And the book might give you this one as a percentage, so you could certainly go ahead and crank that one out if you want to on your calculator. 30 says the probability that they're not taking math. All right, everybody in the dark green circle is taking math, so we're not going to count the people in the dark green circle. What we are going to count is the light green circle, because those people are just taking science, and then those 31 people that are going to be miserably uneducated for anything after high school, and that's going to give us a total of 52. And again, we know what the total of all of the students is. That's 147. So 52 out of 147. Those poor people, they're not taking math. Oh, I ache for them. All right, number 31 says the probability that they're taking math but not science. Okay, well, we've got that in the Venn diagram. That's the people in the dark green circle that are not in the overlap. So that's just the 43. So that'll be 43 out of 147 people. That'll give us our probability there. And then 32 says the probability that they're taking neither math nor science. And like I said, these are the pathetic people that are going to be undereducated for everything out there in the real world. That's 31. So 31 out of 147. So Venn diagrams work really nicely for probability if you can figure out how to read them. All right, number 33, a lottery. Ooh, that sounds good. All right, 33 says we've got a lottery with 53 numbers from which 5 are drawn at random. Each number can only be drawn once. What is the probability of your lottery ticket matching all 5 numbers in any order? Oh, when that day comes, you're not going to see me the next day in school. Now, let's take a look at the total. 53 numbers to draw, and 5 are drawn at random. Now, it doesn't matter what order they're in. It doesn't say there's a Powerball or anything fancy like that we're looking for. It's just saying you need to match the numbers. So out of those 53, if we don't care about the order they come in, we're going to use combinations, C. And they're going to choose 5 of them. So our total is going to be 53, choose 5. And then you need to think, how many of those are going to match your numbers and your numbers alone? Only one. Only one of those tickets had those numbers on there. So the probability of your lottery ticket matching all 5 numbers, well, punch that one in carefully. 1 divided by, parentheses, 53, choose 5, and you're going to see how miserable your chances are right there. So let's change this into a percent. Maybe it'll look a little better. We move the decimal over 2 places. It doesn't look a lot better. And this one again, you know, is talking about 53 numbers that they're choosing from. So they always say, you know, better chances you get struck by lightning than you win the Powerball or Mega Millions or one of those things. All right, so I better keep teaching for another day. Then, the rest of these, I thought you could make your way through pretty good. So hopefully this will go well.